Hello world, and welcome to the sixth and final video in this series on creating an IK-driven procedural walk animation. In today's video, we'll be enabling the rest of our spider's legs, and we'll also be making sure that the orientation of its body matches the terrain. We'll also be fixing a problem where it was sticking its leg through a wall and adding a small walk sound. Come along with me. My name is Marnie and I make games. Previously on Marnie Makes Games, our protagonist, the two-legged spider, was wandering through the dark, misty forest when suddenly he encountered a hill, walked up it, and stuck his leg through the wall. Okay, so maybe that was a little dramatic, but we do have a problem to solve here. Let's see if we can figure out what's causing it. If we look at our rig over here, let's just walk back up the wall. Because the body's orientation doesn't change, it ends up sticking the foot placement target and the casting origin for foot number 8 straight through the wall, which means that now when you try to do a ray cast for the ground, the ray cast goes from here to here with a length of 5 units, which means that it hits absolutely nothing. And if we hit absolutely nothing, our foot returns to its default position according to the code we've written, or it will just try to reach position 000 if we'd written our code differently. Either way, this is an undesirable result. So how do we fix this issue? Well, we'll be going back to our old friend Mr. Raycast. But when we hit the ground, instead of getting the position of the hit, we'll be getting something called a normal. Now, according to the Unity documentation, the raycast hit 2d.normal gives us the normal vector of the surface hit by the ray. So what's that? The normal vector of a surface is the vector that points outward perpendicularly at a given point on that surface. This vector can be useful in raycasting as a way to determine reflections or ricochets from projectiles, or to align a character so that it stands upright on the surface. Sounds pretty useful in this situation. So let's go see how this is going to work in code. In my movement script, which is still attached to the head of the spider or the head bone, I've added some parameters. So I want to do a ray cast, so we need a ray cast depth to tell us how long the ray is going to be. We need a layer mask so that we only get hits from our terrain layer. We need a rotation rate to tell us how quickly we can rotate. And we need a target rotation, which is set up as a quaternion. I've also initialized that so that we don't have any null errors. Now, going to update, the last step in my update is going to be to call set rotation, which is this function I've written over here. Here in set rotation, we declare a raycast hit 2D. We call it terrain hit as before. And now we're casting a ray from the position of the body in the opposite of the up direction, so the down direction for our rotation. And we make our ray the length of ray cast depth, which in this case is 5. And we filter our hits for the terrain layer. Now, in case you didn't know, if you take any vector and you multiply it by -1 to change its sign, or just put a minus sign in front. That gives you the opposite vector. And since Unity doesn't have a transform.down, we take negative transform.up to get the vector pointing down from the head. In here, we check if our terrain hit has a collider. In other words, it hits something and the collider is not null. Then we do something, else we just ignore it. So what are we doing? First, we need to get a target rotation. Now we know that we want the normal of the ground to be pointing in the same direction as the up for our body. In other words, we want to orient the body to match the ground's rotation. To get our target rotation, we use quaternion.lookRotation, and we give it a direction for forward, vector3.forward, that's the vector pointing straight into the screen, and we give it the desired vector for our transform.up, which in this case needs to match the ground's normal. That will return a rotation to match the ground's orientation. Then we want to set our transform.rotation, but if we set this directly to the target rotation, we're going to get a bit of a jittery movement because the head might jump from -10 degrees to 20 degrees instantly, which we don't want. That's why we use quaternion.rotate towards. Now this basically takes one rotation, which is our current orientation. Then it tries to move us to the rotation that we've requested. It moves by a certain amount of degrees in each frame. So how do we determine this? Well, as always, we take the rotation rate, which in this case we've defined as 60 degrees per second, and we times that with delta time, which is basically the fraction of a second that one frame would take. So if you're running at 120 frames per second, that means time.delta time will be 1/120th of a second. Let's get back to the editor and see how this works. In our editor, we're going to select the head. Then we find our component over here. Our raycast depth is 5 for now, which we're happy with. We need to check and set the terrain layer to terrain to make sure. If this is nothing, you're going to get a nothing every time, and the code will do absolutely nothing for you. And then we set our rotation rate. 60 is fine for now. Let's test this. We'll start our walk. Body's matching the terrain, and no more sticking our foot through the ground. Okay, now there's one more thing I want to do. In our foot mover script, I want to add a field for my body transform, which you'll know why I'm doing this in a moment. And I want to add an audio source so that we can actually play a little sound when the foot hits the ground. We've added our audio source. We go to start and we say audio source equals get component audio source. And then in the play step sound function, which I'll show you where we call it now, we go if our audio source is not null and the audio source is not playing at the moment, we're going to play our sound. Well, the reason why we do it this way is that if you have 8 legs and they're all playing sound at the same time, it might get a little noisy, so you may choose to not add an audio source to 2 or 3 of your legs and then you don't have to change much because the code will automatically check if there's no audio source, doesn't try to play a sound, and you get no errors. Then over here in our update method, right there where we change our step phase to planted is the moment we want the sound to play, so we call play step sound. That's it. Now there's just one last change to do, where we try to find our lift point. We used to calculate it by going step height times vector2 dot up. Now this meant that we would find the difference between our 2 points and then try to find a vector directly above it. Now this is fine if we're on straight and level ground, but what if our spider is almost vertical? Then we're going to have a very strange knee motion where the knee actually lifts higher than the final position. To fix this, we actually take the body orientation, the body transform over here, and we use its up vector, whoops, to determine the direction of our lift. But you might notice a little issue here. Unity is complaining that we are trying to add a vector 2 and a vector 3 together. Now this is very easy to solve. In this case we don't need that third dimension, so we just cast this to a vector 2 like this. Let's save up that code again. Now there's some setup on our IK target. Let's look at the 2 IK targets over here. I'm going to select leg 1 and 2. Then you need to add a new component. If you don't know how to do that, you would go down here and say add component. I've already added the audio source. When you've added your audio source, drag in the sound clip that you want to use for your footfall, and then you disable play on awake. And finally, we drag our head transform, which is up here, into this body transform field here to make sure that the leg has a way of finding the orientation. Right, let's test this code and see what it looks like. That's good. Sound plays when the foot hits the ground. Body still matching. The lift looks normal. I think we're good to go. Now let's just do some tuning here. Firstly, let's enable all the legs on the skeleton. There's our legs enabled. Then I've already gone ahead and created foot placement targets. If you haven't, I would suggest taking the foot placement target for the first leg and just duplicating it a few times and then moving it into the correct positions. For me, I'm just going to enable that. Then we go to the part sprites, which we've organized, enable those so we can actually see the legs. And we go to the IK targets and enable those. Now, as you can remember, on each IK target, you need to set up the audio source, which you can do for all of them at once if you wish to. Then you also need to set up the body transform. Again, you can do that in all of them at the same time by just shift selecting and dragging the body transform to all of them. And then you need to go into each leg separately and make sure that you set up these parameters. So that would be setting up its own foot placement target, making sure that you get the cast position dragged in there. The terrain layer should already be set up. If it's not, make sure you grab the terrain layer there and then set up the opposing foot. In my case, I've set up 7 opposite 2, 6 opposite 3, and 5 opposite 4, and the same 4 opposite 5, 3 opposite 6, and so on and so forth. Alright, let's see what's going on here. We're getting an error here, but that was just because our bones were enabled before our sprites. This should be fixed by now. Okay, let's get our spider walking. This is not terrible. I want to make a little change, and I want to tell you about something I did before. If you look at my foot movement scripts, you'll see that I varied the foot speed. If you take all the feet together and you make them the same speed, you sometimes end up with a situation where it almost seems like the left bunch of feet are moving at the same time, and so are the right. I'll demonstrate this in a moment. Let's do this. We're doing it in play mode, so I don't have to undo it again. I can just stop the play mode. Let's do a little walk. I like the variability of having different foot speeds. And then you might also notice it seems like our spider's dragging its knees on the ground. That's quite possibly because the body is too close to the ground. So we'll fix that in a moment. We'll do this. I'm just going to grab my legs over here. Here we go. And move them up. Maybe like this. And let's see what that does for us. I think that's a lot better. From this point on, the spider is in your hands. I've put the link to the Github project in the description. You can do whatever you like from here on out. Use your imagination. Slow down your foot speed. Turn your spider into a squid. Maybe put a collider on your body, and when something enters that collider, have the feet reach towards it. You know, maybe put your spider on a web, and when it gets close to its target, 2 of the feet will reach out, or whatever you like to do with it. It's all up to your imagination. If you do something interesting, leave me a link in the comments so I can see what you did. If you liked what I did, give me a like and subscribe. For now, I am Moni, and I'm saying goodbye.